So to solve a logarithmic equation, we could use the cancellation property that if I take an exponential base a and raise it to that logarithm, it will cancel and leave me with x, just like that. Very similar to how we solve exponentials. But basically, let's look at, no pun intended, let's look at a few examples. So say I had that log x is equal to 2.9. This is base 10 because it's, again, whenever we don't have the number there, that's called the common log, implies it's base 10. But if I apply base 10 to both sides, like imagine I put a 10 there and I raise that log to an exponent on both sides, this would cancel by the cancellation property. And basically, again, I'm not doing this on purpose. Let's imagine doing that. Like let's say, and in the verb term for taking an equation and raising it by a base power is called exponentiating. But if I exponentiate this equation, I would need to do, again, I need to do the same thing to both sides. I would do 10 to the log x is equal to 10 to the 2.9 power. And notice that if I ignore the base 10, this is the same equation, log x is equal to 2.9. So the sensibility of why this works is just because, well, I did the same thing to both sides. If this is equal to this, well, 10 to that is equal to 10 to that. But again, the reason why I'd want to exponentiate both sides is because 10, an exponential and logarithm functions are inverses. They will cancel themselves out when composed together. And that will leave me with just x. And so x will be equal to 10 to the 2.9 power, which again, I could leave that as is for an exact value, or I could approximate that with the calculator. 10 to the 2.9 is approximately equal to 794. And again, I could figure out, well, what log of what is 2.9? And again, I could verify my equation is true by plugging it back in and seeing log of 794 is about 3, or 2.9, I mean. So looking at a few other examples, the key is if I want to solve a logarithmic equation, I can exponentiate using the base of the logarithm. So here I use base 10. Here I would use base 8, because if I take 8 and raise it to the log 8, and again, I would need to do the same thing to both sides, 8, raise it to the 1/3. This will all cancel, and it will leave me with x minus 4 is equal to 8 to the 1/3. And remember, the 1/3 power is equal to the cube root of 8, which is actually just 2. X minus 4 is equal to 2. And I could add 4 to both sides to get 6. And of course, I could check my work in my with a calculator, whatever else. But yeah, exponential. Now there's another way that you could approach these questions, and which is I think more commonly done, which is by using the definition of the logarithm. Because by definition, the logarithm, you can swap the input and the other side of the equation and turn it into an exponential. But that's not how I like to do it. So if you learn how to do it if you learn how to solve these by using the definition, that's totally fine. I just prefer this tactic because it is more algebraic in nature. And if I was to try to solve an equation involving a natural log, since this is base e, that's always what you want to remember about ln. You can imagine there's a little mini e there always. I would need to use e to cancel out ln, and I would exponentiate both sides by base e. So raise both sides to the power based on e. And e and ln will cancel each other out when they are stacked like so. And that would leave me with 2x minus 5 is equal to e to the 7th power. And since e is base 2.72 approximately, this is going to be a very large number. We could go ahead and figure out what that is. About almost 1100. But it might be better. What's more common is just leave it as e to the 7th power and solve. Well, I could add 5 to both sides. That would be e to the 7th plus 5. And then divide by 2. And just leave it sort of like this as an exact answer. Or obviously I could add 5 and then divide by 2 to figure out what is that approximately equal to 550.8. But, you know, sometimes it's nice to have an exact algebraic answer. And let's say we were trying to do an applied question, like in your activity for this week, or that's due tomorrow. But if you're watching these later, it might have already been due. I asked you to figure out the doubling time of an account which was compounded continuously. But basically, if you're trying to solve time frames involving exponential function, if you're trying to solve problems involving exponentials and logs, this idea is critical. And let's look into this. So let's say that you're investing $10,000 into an account that has interest rate of 4%. Let's assume it's compounded continuously, but basically let's just say it's growing exponentially, which is how interest almost always works. Now, it's not usually continuous, but it's a good approximation. It says find the time required for your money to double, aka what's the doubling time in this sort of situation. So basically, our principal value is 10,000. So the future value of our account at time t is going to be given by, well, it's 10,000 times e to the r, and r is the interest rate, which is converted to a decimal, 0.04 times t. And basically, double would be, well, obviously we're investing $10,000, double would be $20,000. So the idea is, well, we want to know how long does it take for the future value to be equal to 20,000. Or essentially, I could plug in $20,000 on the left-hand side because that's my desired end value. And what I want to know is what t would create $20,000 as the future value. And notice what I end up getting is an equation where I want to solve for t within the exponent, very similar to these sorts of equations up here. But if I want to solve such an equation, the first goal is to, well, I have e to a power. The way to cancel out e is by ln. But another thing that's important is you always want to isolate the exponential. Like if you look at all of these examples, you want to get the function by itself before you use. So if you have a logarithmic or exponential equation, you need to get them by themselves first, then you apply this idea of the base of the inverse function. So I would essentially what I'm saying is divide by 10,000 first. 20,000 divided by 10,000 would just leave me with 2, but I'd end up with 2 is equal to e to the 0.04 times t. And also, doubling times will always work like this. You want to know what rate will, given a percentage interest rate, how long does it take to double? It should always be e to the blah equal 2 for continuously compounded. And, excuse me, from here, I could apply the ln to both sides as we did above, because now I have the exponential function all by itself, and the way to cancel out e is by using its inverse ln. Ln and e cancel, which would leave me with the equation ln of 2 is equal to 0.04 t. Now to finish, and again, I've gotten t out of the exponent, which is the goal. I'm trying to solve for t, and I could progress in such a way. Now to get rid of the 0.04, I would divide by 0.04. So t would be equal to the natural log of 2 divided by 0.04. Or if you want to memorize this, the doubling time for a count is always ln of 2 divided by the interest rate. And again, this is for continuously compounded accounts. So this would be doubling time. And there's other formulas for doubling time. When it's compounded in other ways, you could look up the formulas online for such things if you care or if you need them. Anyways, the natural log of 2 divided by the interest rate would give us approximately 17.3, and this will be in the same time frame of the original account, which is in years. So essentially, it will take that account about 17 years to double. And again, I could check this out to make sense by saying, well, my principal was $10,000. It's compounded continuously e to the 0.04 times t. And if I plug in 17.3 years, this should double. And notice it gets me to approximately $20,000. Makes sense as the doubling time.